And I asked Marco, am I right about the presentation about SmartNet project that I well known?
Hello, can you hear me?
Yes.
Excellent. So thank you for the introduction. My name is Marco Rossi and I am from RSC, SPA, which is a research center operating in Italy. And I'm mostly responsible of distribution network modeling and also interaction with the transmission system, especially in the optics of TSO and DSO coordination schemes. In fact, RSC led the project SmartNet, which is an European project funded by the Horizon 2020 program of the European Commission and started on January 2016 and ended the last year. It involved 22 partners from 9 different countries, and thanks to their experience and knowledge, and also the fact that they are very active in the field of electrical engineering and electricity work, since most of these partners are network operators, both transmission and distribution, we were able to, let's say, draw practical conclusion on the, let's say, on the experience of implementation on TSO and DSO coordination scheme. In fact, thanks to the project SmartNet, we joined, let's say, the experience from 3 practical projects. One located in Italy, which is consisting in monitoring and control of distribution resources, and in order to provide services to the transmission system. Then we also investigated the flexibility of domestic loads in order to provide balancing services to the transmission system, but also considering the limitation of the distribution system. And then we also investigated the potential of the backup batteries of the, let's say, of the telephone company Vodafone, in order to provide services to the distribution network. In this case, I'm talking about the radio base station, so the repeaters of the cell phones that are used in order to, let's say, modulate the active power exchange in the distribution network. But this is another story, and you can find all the information that you need and all the conclusions related to the practical experience of the pilots in the SmartNet website. The presentation of today is focused on the conclusion that we draw from the experience with a large-scale simulator, which has been developed in order to calculate for these 3 countries. So basically, I'm talking about Italy, Denmark, and Spain in the 2030 electricity scenario. And we investigated different coordination schemes. So I would like to thank you, Arthur, since he already provided many information on the possibility of, why it's not moving the slide, okay, on the different possibilities that can be exploited in order to make TSO and DSO communicating in order to, let's say, collect the services from both transmission and distribution services. In particular, we consider 4 main schemes. The first one is coordination scheme A, in which the TSO is procuring services from both distribution and transmission services for balancing and congestion management of the high voltage network. For coordination scheme B, we introduced a local market in which the congestion management at distribution level is managed by the distribution system operator, and also the TSO is aware of the activation that has been made by the local market, and it manages also the remaining resources that have not been used by the local market in order to activate services for the high voltage network. Coordination scheme C is basically the same principle of splitting of the high voltage and medium voltage markets, but in this case, also the balancing of distribution network is considered. So this is a scenario in which the distribution system operator is in charge of, let's say, balancing the network, the distribution network, by imposing and activating resources in order to have let's say, a fixed power exchange in correspondence of the primary substation. And then finally, we have probably the most challenging coordination scheme from the computational point of view, which is coordination scheme D. In this case, there is a central market that is managing both transmission and distribution system services. I would like to take advantage of some of the questions that has been asked for the previous presentation in considering, let's say, the aspect that some data of the distribution network are confidential and cannot be shared with the transmission system operator. So in this case, we also investigate this aspect in the SmartNet project, and of course the details can be found in the deliverable. We carefully consider this problem, and we also identify some methods that allow the sharing of information without, for instance, sharing the configuration and the position of the resources in the distribution grids by using aggregation techniques that allows, let's say, the maintenance of the confidentiality of the data, and at the same time the effectiveness of the results of this aggregation. So let's go to the aspect that we consider for the construction of the 2030 scenario and the investigation of these 4 coordination schemes. So basically, in Italy, we identified, according to our investigation, we consider mostly the ENSO visions that we have for these 3 countries. In Italy, we are expecting large volumes of flexible technology located at distribution level, and mostly is represented by photovoltaic generation. And we consider also the curtailment of distribution generation as a potential source of flexibility. For this reason, we see a good potential for both transmission and distribution services for the distribution resources. In Denmark, in spite, most of the reserve, the flexibility reserve is located at distribution level. It consists mainly in resources that have a limited flexibility. In fact, let's say for Denmark, we are considering flexibility from heat pumps and electric vehicles with, for instance, constraints in terms of discomfort for the final user of the heat pumps, or in terms of charging limitation for the electric vehicles that have to be ready at the given time. For Spain, we have more or less the same situation that we are expecting in Italy, but just a smaller amount of flexibility located at distribution level. And we are expecting very different results in terms of efficacy of the different TSO and DSO coordination schemes. So going to the structure of the simulator, we consider 3 layers, and these 3 layers are the market, the bidding and dispatching layer, and the physical layer. So the market is simulating the market clearing routines, which, depending on the structure, are only central market in case the TSO is managing the market, or central and local market in case also distribution services are involved. The bidding and dispatching layer contains the routines that are needed in order to aggregate the physical resources and to interface the physical layer to the market layer, and also dispatching the commands provided by the market. And finally, we have the physical layer, which is simulating the physics behind the resources that are controlled by the market and the bidding and dispatching layer, as well as the network components and the simulation of the grid behavior, which is depending on the power flows on it. So as you can see from the slide, there are different the possibility of selecting different time dimension according to the construction that we selected for the simulator. So we have the time granularity, which is the time resolution of flexibility bits, which is, for our simulation, we selected 15 minutes. Then we have the frequency for the collection of the bits and clearing of the market, which we selected 16 minutes. Then we have the market latency, so how much time the market is taking in order to process the bits and provide the final result, which is being selected to be 15 minutes. And then the market time horizon. In fact, we consider a market clearing algorithm which is also able to consider the dynamics of some flexibility bits, and we so in case there are some rebound effects to be considered in order to allow some resources to provide flexibility, this can be considered by the market. So after the let's say the introduction of this structure, we can go one by one to the layers in order to see which are the working principles behind them. Starting from the bidding and dispatching layer, we consider different routines which depending on the typology of loads or typology of flexibility or generators, they can run their optimization routines in order to interface this flexibility with the market. So we consider as kind of resources and aggregation routines the provision of flexibility from conventional generation and CHP, which is the state of the art, nothing new until now. Then we consider also the atomic loads, so the optimization of activation time deferral to provide the desired power flexibility. And this is the case of domestic appliances, for instance, in which the washing machine or the dishwasher or any kind of load can be activated with different activation time. Then we also consider thermal loads, in which the aggregation routines are based on the monitoring of the indoor temperatures of say building and the remote control of heaters and air conditioner. Then we also consider storage-based devices, mostly based on electric vehicles at distribution level, but also the hydro pumped generation for high voltage networks. And then finally, we consider the curtailable generation and load, which is the application of curtailment to generators, which are mostly renewables, and some kind of loads, for instance, lights that can be dimmed according to the necessity of the market. After the bids have been constructed by these routines, these are processed by the market clearing algorithms. And this is the way the market is clearing, let's say, the received bids is depending on the TSO and DSO coordination schemes, which is basically defining the responsibility of the network operators and the services that have to be carried out for the different voltage levels. In particular, we consider a combination of DC optimal power flow for the TSO services, so for the high voltage network, and a linear optimal power flow for the distribution service. In this case, the two, in particular for coordination scheme D, in which the both distribution and transmission services are managed by the same market clearing algorithm. These two optimal power flow model has been merged in a single model in order to solve simultaneously transmission and distribution services. So the optimization algorithm has been developed in order to provide an objective consisting of the maximization of the social welfare, and it is aimed to solve the predicted imbalance and congestion within the market time horizon that we investigate, I mentioned in few slides above. In particular, I'm showing you some of the results of this market clearing algorithm. This is, for instance, the case of coordination scheme A, for which I remind you that is not considering the distribution services, but you can see that large volumes of activated resources, large volumes of distribution resources are activated for transmission services. This demonstrates that distribution resources has a good potential to be competitive with respect to the transmission network resources. You can also notice that there is a simultaneous activation of upward and downward resources, and this is the case when we have a severe congestion that has to be managed with a simultaneous activation of the resources in both the directions. Then if we are considering instead a coordination scheme in which the distribution services are integrated, this is the case of coordination scheme D.
Marco.
Yes?
2 minutes. You have 2 minutes more.
2 minutes. Okay. Sorry for that. So in this case, we have coordination scheme D, in which we can see there is a disactivation that is downward, and this is the case of curtailment of PV power plant, which can be recognized by the shape, etc. So basically, this is the structure on how the physical layer is constructed. So we have the optimal power flow for a distribution network, in which the optimal power flow is, in this case, is the minimization of the set points provided by the market, minimization of the deviation with respect to the initial set points, and then we have also an optimal power flow that we have for the distribution network, which is, for the transmission network, which is considering the power exchange between transmission and distribution, and it returns also the residual imbalance. So at the end, in order to investigate the potential of the different TSO and DSO coordination schemes, we consider the cost for balancing, so the activation of manual frequency restoration reserve for balancing and congestion management, the cost for information technology, which is dependent on the market clearing algorithms, and then the benefits considered as the reducer residual imbalance, which is being monetized by calculating the amount of secondary frequency restoration reserve. So basically, if you're looking at the results, we have that for Italy, in which there is the need of distribution services, coordination scheme D, in which we have both the services, and coordination scheme B are the most profitable one. While coordination scheme C, which is adding the constraints of balancing distribution network, is the worst. For Denmark, we have the opposite trends. In fact, there is no need of distribution services. And in this case, what is making the difference is the additional information technology cost. So we have more or less the same cost for balancing and congestion management, but higher cost for information technology. And this makes coordination scheme A the most profitable one in case for the Danish case. For Spain, we have more or less the same results that we have for Italy, but in this case, let's say the benefits provided by the more complex coordination scheme is basically cancelled by the additional IT cost. So this is my conclusion. So in case the probability of distribution congestion is comparable to the forecasting error, TSO-DSO coordination scheme A is the most profitable one. So there's no need of activating markets or services for distribution services. In the other cases, coordination scheme B and D, which is depending on the confidentiality and the complexity of the system, have to be selected in order to provide tangible benefits. Then coordination scheme B, of course, is less efficient than coordination scheme D, since it splits the same problems into two different optimization problems, while coordination scheme C, as I said before, is introducing a stronger constraint in the optimization problem, which is the distribution service balancing, the balancing of distribution networks. So it does not to be considered. And there are also literature that is demonstrated that even in case the resources are enough to provide this kind of services, coordination scheme C is not profitable. And then finally, we demonstrate that distribution services can be cost effective and are competitive, and distribution resources can be competitive with respect to transmission resources. Local market, of course, suffer of liquidity problems, and central markets are the most complex, but of market demonstrate that can be tractable and can be promising for TSO-DSO coordination schemes. So sorry for being long.
Thank you a lot, Marco. Yes, we are short in time as usual, but your presentation is very interesting and compliment for the work in the SmartNet project. We have time for very few questions. I tried to make a sort of summary of the questions that was run by Dan and Nando. Basically, the focus is you are mixed together transmission distribution. If you can have a look, basically the question is about the use of three-phase models on the distribution network, since you were using also domestic loads.
Yes, correct. In this case, we didn't considering the phase balancing as a service, so it's a role of the DSO to keep to keep, let's say, the three phases balanced. Insofar this, let's say, the inverse voltage, let's say, the inverse power requirement is respected, let's say, we can neglect the aspects that, let's say, we can neglect, let's say, the influence of the single phase loads on the three phase. In addition, if we are considering a delta star connection in the secondary substation, this aspect of the phase balancing is further mitigated. So we didn't consider the balancing of the phases as a potential.
So you didn't use three phase?
No, we don't.
Okay. One more question was about which type of simulator you were using, if you were using off-the-shelf tools or
no, it has been developed from scratch. It's open source mostly. We use Python, so it's an adaptation of the math power tool to Python. I think the name is PyPower, but it has been adapted in order to be computationally efficient. In fact, let's say simulating one day.
The network are quite big.
Yes, exactly.
Okay. I think we have to move. I don't see any more questions, but well, there was one question about the heating sector. So what is a multi-energy aspect? But I don't think it was.
Yes, we consider, let's say, the physics behind the different devices. For instance, thermal loads has been considered. So
okay, but it is slightly different.
Yeah, yes, I know, but in this case, we consider only services for the distribution and the multi-domain optimization. The multi-domain consideration has been modeled as a storage-based technology at the end.
Okay. I think we can close. Thank you a lot, Marco.
Thanks to you.